if I had to find like the average value of a function, I'll just write f(ab) between two values like a and b, and these are just two numbers. You know, a is like, let's say a was 2, and the b value is 5. And I need you to find the average value of the function f from x equals 2 to x equals 5. So you don't even have to think of these as a's and b's. Does anybody know the math formula on how to find the average value of the function between those?
Wouldn't it be like f of b minus f of a over 5 minus 2?
He just nailed it. So when he's doing slope, he just nailed it. That was perfect. And good job. He just did slope. And so if he had to find the average value between the value b and a, he goes, he'd get f of b, you'd subtract f of a over b minus a. But do you notice that's just slope?
Yeah.
That's just that one. That's y sub 2 minus y sub 1 over x sub 2 minus x sub 1 for 2 x, y coordinates. So now you're like, oh, now I see y in 2.1, which the author titles the tangent and velocity problems. We're just finding the what? Average value of a function or slope. That's all we're finding. We're finding what's the average value of a function. The average value of the function. And we're like, okay, we don't have to do 100 of these, do we? Well, let's do one, right? And let's do one that has like an A and a B and a C and D. And we'll do it together. That sound good? All right. I'm gonna erase this. This is all we have to do, huh? F of B minus F of A over B minus A. That's how you find the average value of a function. Sound good? The average, and I should be clear when I say this. Not the average really value. Would you write this down? This is what I mean by it. The average rate of change is what I'm hitting on of a function. The average rate of change of a function f of x, the math formula is do f of b minus f of a all over b minus a. That's all we have to do. In other words, slope. So I'm sorry when I wrote function's average value. We'll get to that later in the course. I'm talking about the average rate of change of the function f of x. So on average, how did it change? And we'll do that. Well, hey, so to make this simple to us, this is slope, right? Average rate of change of a function. Let's just do temperature, and then we'll get a sense of this. Remember when at 6 a.m., it was 50 degrees Fahrenheit. 5 hours later, it's 11 a.m. It was 65 degrees Fahrenheit. All right? And my question for you, it's a math question. Can you find the average rate of change of the temperature over that time period? And you're like, yeah, I can do it. And you're, how do you do it? Well, right here. This is all you do. Can you find the average rate of change? The temperature went up, didn't it? But how, on average, how did it go up per hour? And so what can you do? Well, I can think of this as an x and a y, and this is an x and a y, right? It's always good in math to make time x. So, all right, here's my x, there's my y. There's my x, there's my y. I'll put subscripts of 1s here. X sub 1, y sub 1. This is x sub 2, y sub 2. Can you find the average rate of change of the temperature during that time period? And you're like, yeah, no problem. Right? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1, right? That's all we'll do. You might be able to do it in your head. What's 65 minus 50? 15. And then here comes time. 11 minus the what? 6. So I get 15 degrees Fahrenheit per how many hours? Now do you want to simplify that answer?
Yeah.
What could you say? On average, the temperature changed how many degrees per hour? There you go. You can just put an HR at the bottom if you want to put an H. On average, the temperature increased 3 degrees per hour. Did it do that each hour perfectly? No, it probably went up like 1 hour, 1 degree Fahrenheit the first time, and it went up even quicker in the second hour. But on average, what happened between those two, between the 6 a.m. and 11 a.m.? So everyone, pretty easy concept, all right? So like, okay, got it. Well, let's do one problem. Let's do that number 5. Yeah, started to steal the thunder from the problem that I put in the syllabus, but let's do it. Let's do this problem. This is number 5. All right, what do they got here? They got a little math formula. They got y equals. Hey, does anyone want the actual page number? This is on page 86. Someone might not have the textbook. And when I could have chosen 7, I could have chosen 3. I just like 5 because they're throwing a ball. And they throw a ball, and they said it's thrown with an initial velocity of 40 feet per second. And they go, here's the height at time t. So this is the height at time t. Y equals 40t minus 16t squared. So when y is your height, position, t is your time, and this is in seconds. All right, and that represents the position, the actual height of the ball. If a ball is thrown into the air, so the ball gets thrown into the air, it's thrown from the ground, and when that actually deals with the gravitational pull in the earth, that negative 16 right there. Then what you think was thrown off the planet, or another planet, or like the moon. All right, so what they want us to do in this problem, here we go. They said find the average velocity, and they give you 2 time periods. They go find the average velocity for the time period, and they give some a time period. Okay. Well, this is height, right? This is height. And they said, give me the average velocity. Well, average rate of change of function. Guess what is? What's the average rate of change of position? That is velocity. Do you follow me? So I think that's important just to know that. We're going to find the average rate of change of the position with respect to time. We're going to find the average rate of change of position, height, with respect to time, but there's another word for that. And you go, what is that? It's just called the what? The average velocity, right? It's average velocity. That's what we're finding. So this is all we got to do. No, so all we got to do is do f of b minus f of a over b minus a. All they do is just give us the time periods. Okay. So letter I, and this is why I want to do this problem with you, the way that it's described in the book may be confusing to you. They go starting at time equal to 2 and lasting 0.5 seconds. So can I put that in other words? I need you to find the average velocity. This is height, right? Can you find the average velocity from t equals 2 to, how much further do we got to go? 0.5 seconds, so 2.5 seconds. Alright. Then you got to go from 2 seconds to 2.5 seconds. And just find the average velocity. Alright, let's do it. F of b minus f of a all over what? Everyone feel free to use your calculators if you want. F of 2.5 minus f of 2 all over 2.5 minus what? 2. But my rule of thumb is if 2 people get the same answer, then I know it's right. So if somebody else could double check that, that would be great. Now, if we don't get the same answers, then we'll go look at the calculators or how you computed it. These are some weird decimals, so you probably want to use technology on this problem. This is a part B, and it leads to something. So this was actually letter A. Find the average velocity. It's average rate of change in position with respect to time. So on average, everyone, how fast was this ball traveling? Don't be shocked if you get a negative answer too. Because everyone, can velocity be negative? Excellent. So when I threw that chalk on up on the board, whoop, up in the wall, up in the air there, that chalk, when it was going upward, it had positive velocity. When it was going downward, it had negative velocity. Cool. What do y'all get out of this? Anybody get an answer yet?
I got negative 32 feet per second.
Negative 32. Anybody else get that? Oh wait, let's see if anybody else gets this. And you did feet per second. This was feet, this was in seconds. Feet per second. Did anybody else get that? Thanks for doing it.
Yeah, negative 32.
That's it. So we got two people. That's how it always works. You get two people. No way two people can screw up the same way, right? You may say it's likely now. Usually in the class, two people get the same answer. So that's it. So on average, the ball, how fast was it traveling? Negative 32 feet per second. Why is it negative? Well, during that time period, the ball was on the downward path. That's what's going on. It went up for in the first couple seconds, but then it started going down. All right, we get it. All right, well, what do they get to in letter B? They want you to do the same thing. So, and this problem may seem tedious to you, but there's meaning behind it. There's a reason why we want you to keep going through this. In letter B, they go from t equals 2 seconds to how much? 2.1 seconds. Now, do you notice this was tighter? Does someone say this? This was tighter? It was like a tighter region? Okay. So there's a reason why they're doing this. You're like, okay, I'll just go through the motions. There we go. Just do this, right? In fact, we'll skip D, C, and we'll just go down to D. We'll get down there. All right, so that was negative 32 feet per second. Let's see what we get.
I have a question.
Oh, you bet.
So negative velocity means that it's decelerating or something?
Nope. Well, so acceleration, we could talk about how with acceleration and velocity being negative and positive. The key was this, like pretend this was that object that got thrown. I'm just going to throw it up and down right now. I'll make sure it doesn't drop this time of break. When it was going on its downward path, it had negative velocity. And when it was traveling up, it had positive velocity. Now here's another thing. Do you know what the velocity was when it got right at the top?
The peak.
0.
It was 0. It was exactly 0. There was an instant when that chalk reached its top height and then it came back down. So it had, I threw it up, it had positive velocity, got to here, about 0 velocity, came down negative velocity. Now some things, sometimes things move right and left. So when it moves to the right, positive velocity. When it moves back to the left, negative velocity. You can think of like an ant. An ant just crawling on this tray here. So all right, the ant went this way, positive velocity. What if it stopped? 0 velocity. What if it went that way? Negative velocity. Cool? Yeah. Hey, can we get this one?
Negative 25.6.
All right. Get that?
I got
What?
Okay.
Oh, 2, that's 2. Hey, excellent. We got 2, got it. Feet per second.
That's not what I got.
Oh, you got something different.
No, I might have done something weird.
Could be that calculator. Don't worry.
Yeah, it could be.
It's a little more tedious, that's how I grew up.
I got
Okay,
negative
so-
32.
Oh, so it's definitely not gonna be that because of how this was different?
Yeah.
That being a little bit tighter, so probably, you can go back, you'll see where you are, it's probably one of these numbers in there. Did you divide by the 0.1 there?
Yeah.
Oh, good. Cool, it's probably in one of those 2 values that you got. Everyone, I'm gonna skip to D now. C is just like this. Do you notice this got tighter? Closer time period, closer. One more of these, and we'll see where we're going with this. This is the best introduction you can have to calculus. We just need one of these problems. Find the average velocity from 2 seconds to 2.01 seconds.
Oh, I know what I did.
You know what it was? What was it?
No, I know what I did wrong. I did all of these wrong except for the first one being just. I don't know how I got
That's the best part though, you found out what your error was. And when they want you to find that average velocity. I mean, my goodness, that 2 seconds of 2.01 seconds, it's like, right? But this is what we're getting at. This is leading us into calculus. It's still an average velocity, just over such a tight what? Time frame. 0.01 seconds, right? But we're still going to get the average velocity of this ball that was thrown from 2 seconds to 2.1 seconds, right? This is the average velocity from t equals 2 seconds to t equal to 2.01 seconds. And we're looking at these numbers here and how they're kind of going. You have a feeling this is going to be negative? Yeah, me too. These last two were negative. It's probably negative. And when all they're doing is they're using technology just to go, what's f at 2.01? What's f at 2? At least we see the denominator is just a 0.0 what? 0.01, right? Good? Hey, what do y'all get?
Negative 24.16.
Negative 24.16.
I got that as well.
Awesome. So we get this. So this leads us to this. Are you ready? Welcome to calculus. Ewan, can you make an estimate now for me? These are all what kind of velocities? Average. Okay, yeah, average rate of change of position, average rate of change of a function, average rate of change of height with respect to time. These are all average velocities. Can you estimate the instantaneous velocity? That means at one instant, right? At exactly t equal to 2 seconds. But we're saying estimate because you haven't been taught how to do this yet perfectly. That's calculus. But this is what we're talking about. This takes calculus to solve this. But this should give us an idea. Because between 2 and 2.5 seconds, that's the average velocity. Between 2 and 2.1 seconds, that's the average velocity. My goodness, these are like on top of each other, right? This is very close to an instant, right? It came down to this. So if we had to estimate what would be the instantaneous velocity right at 2 seconds, what do you think you'd go? Which one of these answers is the best estimate? Is it that one? No, it's too spread out. You want to get, after all your work, take the tightest answer. So which one is going to give us the best answer? That's okay. If you want to just put that as your answer, that's a great answer. But some of you might even come up with a better thing. You might round it to an integer. What's the closest integer to that? Just think integer. What was that? Yeah, but so I'm going to put that for my answer. Estimate the instantaneous velocity at t equals 2 seconds. I'll draw here. It's like this guy, because that was the tightest range we had, right? The tightest interval to give us an idea at one instant. And I'll just say, okay, so it's roughly about negative 24, and I'll put the units feet per second. I'll put them here too. When I didn't put the units here, I apologize. So you remember that? It's like sometimes we have to do that if we don't have like a math formula in calculus, and we're just trying to estimate an instantaneous velocity, like the instantaneous velocity of a car at exactly 8:10 p.m. Well, then we can get two periods of time that are as close together as possible, and we use the average of those two. We just do f of b minus f of a or b minus a. You'll be shocked, Aaron. And who's going on beyond Calc 1? So you Calc 2? Anybody going to get a Calc 3? Watch how many times you have to do this in Calc 3. Because you'll have a table. You just have a table values, you go, it says estimate the, and you go, oh yeah, I'll just, and in this gigantic table, you're just going to take the two numbers that are closest together. That's all you'll use. Because you'll be like, that'll give me the closest, the best estimate of what's going on in an instant. Cool. But there is a way to find the answer to this exactly, but we're going to use calculus. We'll get to that later. And some of you probably already very curious about that. And that's what we're getting to. So the real idea is what we're getting to is eventually we're going to say, we're trying to find this. This is what instantaneous velocity is. Right, so this diagram, here's where math gets cool. You know, what can we calculus? I guess spell it right. Instantaneous velocity then for this problem would be, okay, keep doing your f of b minus f of what? Keep doing that, right? But it's the limit as the difference between b and a approaches 0. So I'm going to put LIM for limit. It's the limit. And I'll just make a little note here and just say, as the difference between b and a approaches what difference? APPROH. A difference of 0. The difference between the B and the A, that little difference we had there, it was approaching what difference? A difference of 0, right on top of each other. So this is the word LIM for limit, and that's what we're getting to. So the next section deals with limits. We'll spend the next 3 sections just on limits. It's the what? It's the building block to all of calculus, it's that foundation. We're trying to see what's going on at an instant. So it's the limit, and we'll come up with other notation. We'll write this in different ways. Okay? We can write this a little bit cleaner. Because this looks messy, doesn't it? I want to leave it like this, though. I want to leave it right now. I'll put my quotations right now. That's how I'm going to leave it for now, because that's what we're getting. We get an idea of this, though, right? The average velocity is the limit as of this answer, but as which one? As the difference between the B and A got really, really close to a what? 0. We can't say exactly 0 because you can't divide by 0, right? Right now. So we're like as it approaches 0, as it gets as close as possible to 0. Cool? Awesome. Now do you want to see that graphically? I can show you that graphically. What's this graph look like between 2 and 2.5 seconds? Well, one real quick. What's f of 2.5? And what's f of 2? And thanks for bearing with me on this problem. It's just good to take this problem, look at the graph. And we'll see, what does this look like graphically? F of 2.5 and f of 2. What were these numbers? That was 80 minus 64. I know that's 16, right?
Yeah.
All right, what's f of 2.5?
0.
Is it 0?
Yeah.
All right. So I'm just going to plot these. At 2.5 seconds, and I'll just put t down here. At 2.5 seconds, it was right here, huh? This being y and this being t. At 2.5 or 0, what was going on at 2 seconds though? How high was it? 4, 5, 6, 7, 8, 9, 10, 11, 12, go higher, 13, 14, 15, 16, way up here. Somebody get a dot right here. So right there went at 2 seconds. But this ball was falling fast, huh? This ball went like what? It was going like that. Don't agree? And it's like a curve. And when that graph, is that an upward down parabola or a downward parabola? Downward. You all see that. And it was that portion of the downward parabola, right? It's just going like this. And that's representing the height. Well, what were we doing, everyone? We kept getting like this. But I heard you say it. Doesn't just mean slope. Right? So we were getting a slope of what we call, in this case, secants. We started out by getting this slope. That was the first slope. And then when you know what that slope was? That was that first answer to letter A. I think it was negative 32. Do you recall that? But then we took a tighter region. We didn't go all the way from 2 to 2.5 seconds. This time we only went what? 2 to 2.1 seconds? Now, when you okay if I erase real quick? I didn't know if anybody was copying. So that we got the slope of this. But then we go, well, let's go closer. So then we took, you ready? We took a tighter secant. That's called a secant. When you got a line, it cuts in between the curve. Then we took it from what? 2 to 2.1. So here's 2 right here. And we just went to about here. So now the tangent went like this. But there's still a tiny space between this curve and that tangent line, right? And then we said, let's go even tighter. And we went what? With our little secant line. As this curve went like this. We took it even tighter. And this thing went from here and went to the next point right off the curve. And went like this. So we were getting all these slopes of secants, right? Well, in this box is the slope of the secant. And guess what happens when you finally get the limit as the difference approaches 0 between the difference between B and A of the slope of the secant? You know what we were going to estimate? That estimate we got was the slope of the tangent. Because you're talking about, we were trying to estimate everyone. Here's a curve. Let me get this a little bit better here. It was going like this. and you're trying to get the slope of this curve right here at an instant. And that's called a tangent. Because how many times does a tangent hit a curve? Only once. So we were getting all these slopes of secants. Do you follow me? A secant is some line that cuts to a curve in 2 points. But in the end, we estimated the slope of the what? Of the tangent. Do you follow me? So I want you to all see what it means graphically. We were able to estimate the actual slope of just a tangent, a line that hits the curve in exactly what? One spot like that. And that's calculus. So in this case, this part right here was the slope of all the secants. You add this part to it, and you get a slope of a tangent. You follow? Hey, cool. So welcome to calculus, but now we get to spend, the next 45 minutes doing limits graphically. So on 2.2, let's find limits. But which way? Graphically. And thanks for your patience on section 2.1. I know you already know about average rate of change of a function, right? But I want you to see where this was going. We were trying to get the tightest region to help us estimate what's the instantaneous velocity. Alright? And we were trying to estimate not the slope of a secant, but the slope of a tangent to a curve. Cool? Alright, and that's calc. That's cool. Calc, well, we estimated it, but eventually we'll write this better. And I want you have to agree, isn't this kind of sloppy here the way I write this? That's not really like elegant, it's not very neat, but we're going somewhere with this, that's my point. We'll clean this up later when we learn some new things and we can write this really neatly. For limit, we'll just put LIM, but I think we're gonna just write something else right here. We'll write something right here between that. Alright. But you gotta admit, this stuff is pretty cool. Calc is cool because everything else was, everything was a nice slope of a tangent. I mean, of a secant that goes to 2 points in a curve. Now you're getting slopes of tangents. So I'm just going to start out with an image. All right. Let's just say, you got a graph that went like this. Okay, there's f of x. Oh, and this is the x-axis, this is the y-axis. There's my function f of x. And I'm going to ask some questions. We're going to find some limits graphically of f of x. Doesn't see this graphic? Hey, I'll get all the other chalk off this board so it doesn't interfere with our graph. Hey, does that graph pass the function test? Like in an algebra class? Okay, good. Sometimes I'm gonna make sure I didn't draw some goofy graph. Like I couldn't draw this, right? That's not a function, is it? Good. So this is a function. There's f of x. If you want to put arrows here at the end, you can. Just let that thing keep going up. This x value right here, everyone, is x equal to 2. Yeah, making up off the top of my head. This value right here for y is 1. This value right here for y is negative. And you and I are going to answer these questions. Find the LIM. What's LIM stand for? Limit, yeah. Find the limit as x approaches the value 2 of f of x. Put this right next to it. Say with me. Find the limit as x approaches the value 2 of the function f of x. And I'm going to tell you which side. All right? So we're going to do it from the left side. So the notation from the left side is, see this 2 right here? In the upper right corner they put a negative. So that means from the left side. You want to even write that in your notes? I think it's good to know that. Now what's that little symbol right there, that little negative off to the top right? It means not to the left, but what? From the left. That way you're communicating to yourself properly, like if you're doing this on a test, you're like, I have to find the limit as x approaches 2 of the function f of x from the left side. So you get your hands or your eyes, a pencil, and you're going to jump on this function on which side of x equal to 2? This side or this side? You're going to jump on this side, aren't you? And you go, what are you going to do? Are you going to take a nice ride? You go, where do you wanna get it? You get it on the left side of 2. Well, you can start up here, but we were just talking about this. You might as well get really, really what? Get really close. So how about let's jump on right here. I need you to write it in. What y value is it getting closer and closer and closer to? That's the answer. Everyone okay with that? Everyone good with that? You're like, yeah, jump on the left side. I could have started here. You're like, well, you don't have to. Just get really, really close to the 2. Write it in, see what y value is approaching. So you just found, like, what's going on, what y value is that getting closer and closer to as you approach that? Alright, cool. Not bad. This is limits graphically. Here's my next one. They go quick. This time I put a plus in the top right corner of that too. Guess what that means? From which side? From the right side, if you want to write that down. So when I need you to hop on this function, from the right side of x equal 2. Over here, right, you can, but you might as well jump really close. That's what we're talking about. We're getting really, really close to 2. And write it in. And of course this, we haven't done this before, and there's an open circle there. But remember, the word is approach. That's why calc is cool. I want to know what's it getting close and closer to as you approach 2 from the right side. Let's do it. As I get closer and closer and closer and closer and closer and closer to 2, what y value am I getting closer and closer and closer to? -1. You go, yeah, but at exactly 2 it doesn't exist. Who cares? It's a limit. We don't care what's going on exactly 2. You follow me? Oh, cool. So let's put that answer down. It's -1. Now here's a powerful statement. How about LIM, limit, x approaches 2, and I don't put a plus or a negative up there. That's called a two-sided limit. So, and that's called a two-sided limit. Now it's powerful. The only way you can get a numerical value out of this is that the left side and the right side limits are the same. So that's the only way I can put down a number here. All right, I can put a number right there. If these two numbers are the same. Well, they're not, so guess what I have to put? Yeah, it does not exist. You want to write DNE for it does not exist? You want to write non-existent? The two-sided limit does not exist. The only way it could exist, the only way, is if these two numbers what? Are the same. And that would be my answer.
What's the open circle mean?
Great question. Open circles on graphs. We really emphasize it with this open circle. It means there was nothing there. It didn't exist there. Assuming when I say it, the function's value. So the actual function's value. So at x equal to 2, like this. And I know this is neat because this is a calc question. According to this graph here, what is f of 2? So this is pre-calc. So anyone, I encourage you, that was a great question. Add this to your notes. Pre-calc question. There's the graph. Look at that graph carefully. What is just f of 2? You should be able to find it. And you go, well, there's an open circle there, so I can't use that. Well, where's it filled up? Right there. Cool. By the way, this is interesting. On my first test, Tuesday, students, and we did, yeah, on next Tuesday, students don't miss these. This is the one you miss sometimes. You won't miss it. It's like a student misses class. They'll miss the pre-calc question. They'll go and they'll go, it seems like it's broken up here, so I can't put anything. And it's like, no, you gotta look for that dot, right? Awesome. Oh, question, go ahead.
So if you ask the question without the negative or the positive sign, we have to first of all find the negative, then the positive.
I love it. That's how you gotta think. He goes, you gotta look from both sides.
And see what it's equal to.
That's right. So everything in this course, if you're looking at something graphically, and they just do something like this, and there's nothing up there from the left, from the right, you're like, well, I'm gonna have to look approaching from both sides. I have to think about what's going on both sides. As long as if it's a straight line, no, I'm fine. It's going right through it, so I'm good. But that's how you got to think about it. It's very powerful when they do that. That's very good. That's very good. Hey, here's my next problem. So it's going to change a tad. Oh, go ahead.
If they were equal real quick, so if it's 1 and 1, then the limit.
Limit would be 1. Isn't that cool? It's actually a theorem. If you want to make a theorem out of that. You're like, if this limit right here is equivalent to that limit right there, then limit as x approaches 2 would equal that number. You can call this like C. If that's C and that's C, then limit as x approaches A is also C. And you can make a theorem out of that. Isn't that cool? Awesome. Now watch this. I'm going to change one thing. You're going to tell me what happens with all these answers. this one, and your cool question, I'm included, so include his, here. A, B, C, and that's D over there, right? Here's my change. So let's erase all the answers. And here's my change, are you ready? That's my change. So to get this whole section now, we just gotta change little pieces. So that's not filled in. I don't know if that looks like there's a hole in there. There's a hole in there. Take that chalk off there. I'll use this thing. Make it go away. There we go. That's better. So I got two opens there. Hey, it still passes the function test, though, right? All right. What's the answer? Write it in. Limits x approaches 2 from the left side. All right. There's x equal to 2. I jump on the graph, close. I approach in. What's it? Remember, it's all about limits. It's not who cares what's going on at exactly 2. It's about as I'm getting closer and closer, as close as possible. What's it keep getting closer and closer to?
1.
That's it. Same answer as before. What's this answer right here? Right? -1. These don't equal. What do y'all think? They're not equal. Doesn't not exist. I guess we're getting all the same answers. Well, except for his question. Come on over here. What's f of 2? Now that means what's going on at exactly x equal to 2, what's the function value? I see 2 holes. So what do I put here? There you go. Undefined, does not exist. Right? Is that cool? Awesome.
And if they're both equal from the left and from the right, what's the limits for the third option?
Oh, this guy right here? So if that was, let's say it was 5.
And the second one?
And this one was 5. And boom, 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 that's a 5. Isn't that cool? We'll do one of those too. I love your curiosity. We'll do one of those. We'll make a picture of that. We'll see what it looks like. Awesome. And I have to do one more of these, ready? Ready? This is 4. There's my dot. Okay, what goes on with this problem? Does it pass the function test? Yeah, it's a function. It's a function, right? Draw vertical lines, only hit it once. Well, aren't these 3 answers the same again? What's that then now? But see, the pre-calculus is whatever it sometimes get everyone. You get all 3 answers the same about the approach, but what's this now? It's way up, it's a 4 now. It's up there. And this funny, this had nothing to do with these. Welcome to calculus. This had none, that 4, you know? That was going exactly at that.
It's just a dot, which is pictured as a straight line, I guess.
That's right. That's a good way to look at it. That was good. All right, I gotta do your scenario. Are you ready? So this was yours, and it was a good idea. Oh, what's the name again? Arnold. I'm doing yours. Here it is. You ready? I'm keeping that there. I'm just gonna go like that. All right, let me wipe out all the answers. You ready to do this? Get your eyes on that curve. Jump on the roller coaster. Approach 2 from the left side. What are you getting close to? From the left, what are you getting closer to? 1. How about from the right? 1. These are the same. See, people get worried about this. They think, oh, I should put D and E here, because they see a hole here. But no, 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 no. What's this answer? By this theorem. If that's a 1, that's a 1. What does this have to be? And we can see it actually. Can you all see this? As you approach 2 from both sides, the function kept getting closer and closer to a what? To y value 1. But there's a hole there. It's all in the approach, as infinitely close as possible. Right? This is still a what though? It's still a 4. Isn't that cool? Isn't that interesting? Don't think like here, oh, it's got the open, I have to put D and E. Absolutely not. If these are matching. It could be a nice hole there. That limit exists. The limit exists, doesn't it? Cool? But what was f at 2? 4. Alright. Now watch this. Which really means that when I just did that, then basically this is nice and what? Smooth through there, okay. So they did it right through there, went right through that for him. So do these stay the same? I don't see an open circle. Well, let's still do it. As you approach 2 from the left side, what are you getting closer and closer to? 1. As you approach 2 from the right side, what are you getting closer and closer to? 1. Those are the same, so the limit from both sides has to be a what? 1. Now what's this though? 1. Don't agree? 1, 1, 1, 1, 1. So this must be building into something else in calculus at school. It is. Unfortunately, when we're in section 2.2, that's in section 2.5. Maybe they wait too long for that. You know what that's building on? Do you notice that the curves like connected? They call that continuity. So when something's going, what we just saw, if you have to define, like in calculus, how do you define continuity? How do you define that a function has to be continuous? We got to explain this in theory. The idea that what? This limit right here, it's the same for both sides, this number, and it has to equal to what? The same value there. And that makes it all what? Nice and connected. Isn't that cool? That's how you actually, in mathematics, in calculus, you define continuity by that concept. We just got to write it with goofy notation, right? We just got to, the idea that these limits have to match the what? These numbers right here have to match, for this to work. What did I have before? A 4. You go, is that connected? No, it's not connected, right? Think of this as a roller coaster. It's not connected, it's not continuous. You'll fall in the hole and you'll die, right? But to make this thing connected, that value there has to match what? This guy. Isn't that cool? And if you get that right there, and that, you got it. Now don't worry, that's coming up, not today. That's section 2.5. You're saying, oh, you got the function being continuous. Isn't that cool? So that's how you define this word continuity in continuous functions. Evan, I think we've hit every scenario, but I'm still going to put some other graphs up here, okay? I think we hit all the scenarios, right? It's like nothing should be able to stump us. Well, what about like asymptotes? Have you ever seen asymptotes before? I mean, the book's going to get into that. I think he waits too long, but it's okay. He waits till this section to get here. I don't think it hurts us if we just look at some pictures of graphs of asymptotes. Do you? I don't think so either. So let's just draw a graph, and I'm going to make one up. Ready? Well, in fact, I'm going to erase this. Find a limit as x approaches the root of the function. Let me look for a good one. How about 2 over x minus 3. Now, if you want to make this graph with your calculator, you can, but now notice I put the function in here. I want us to find this. I'm going to do one more thing though, okay? I'm going to do a little minus there. So you and I are trying to find the limit of this function equal to 2 over x minus 3 as we approach to the x value 3 from which side? From the left. And you're allowed any way you want to do this. You can use any technique on your test to do this problem. But I encourage you, you all are so good at graphs. Why don't we just make the graph and look? Right? You go, I don't know how to graph that. Oh, we can graph this. This is called a rational function. Remember, they got asymptotes. And it's got vertical and horizontal asymptotes. So we got to talk about, in this rational function, let's just go over here, a little pre-calc review. A little review of pre-calc. How do you graph the function f of x equal to 2 over x minus 3? So you and I can look at this graph so we can answer this question. Because I want to answer this question graphically. You might have other ideas, and I think that's good, actually. You might go, I got another way to answer this question. But we're going to answer this question graphically. Well, I just need to know how to graph this. Well, that's called a rational function. And it's got, first of all, a vertical asymptote. Find a vertical asymptote, but we got to set the denominator equal to 0 and solve for x. So what makes x minus 3 equal to 0? Alright, so when there's a vertical asymptote at x equal to 3, let me just draw that then. Alright, so this graph. Aha, now you know why I asked you what's going on at 3. Here you go. That's a little vertical asymptote. That just means the graph's going to curve and bend into this thing like that. Now, does it have a horizontal asymptote? Yep.
Yes.
You know what it is?
0.
Man, you're good. A lot of people don't know this. How'd you know that? She just knows it, right? She just, that's good. She knows her pre-calc. Oh, and if you want to know with these rational functions, if the higher exponent's on the bottom, it's always y equal to 0. So the horizontal asymptote is the x-axis. But if you want to know something, if you're like, oh, I forgot that pre-calc, or You know, it's just been a while since I had pre-calc, like a year. Like Jordan is like, oh, it's been a year. If the higher power of this exponent, see that little power right there? If the higher power is in the denominator, then you always got it at y equal to 0. Cool. That's what the horizontal asymptote is. Now, if you're curious, like, well, what if the powers are the same? We'll get into that later this week. We'll get into that later this week. We don't have to harp on that now unless you really were curious and like, no, tell me about it now.
You said it equals.
Yeah, you do stuff like that, yeah. And it's, see, they really get into this in 2.6, I just thought it'd be neat to talk about it right now, since we're doing limits graphically, right? So, where's the horizontal asymptote? Right here. And it's always gonna be here in a rational expression if the higher power of the exponent is on the bottom. Alright, so there it is, but how do I get the graph going? I wanna make this graph. And some of you are like, well, I use my graphing tool. Okay, that works. But let's say I have this calculator, and I can't make the graph. Can I hold it up?
Yeah, hold my joke.
Oh, yeah, but so I don't have the graph, so I'm gonna have that thing, I gotta make this graph on my own. So I got the hardest part done, I just gotta plot some points. I think I can do it with 2 points. Let's make a little table. Just pick an x value on this side, and this value is 3. Like, what's going on at x equal to 2? And what's going on at x equal to 4? I'm just trying to make the graph, right? Well, I think with 2 points I can make this graph. What's going on at x equal to 2? I get -2? Did I do it right? What's going on at x equal to 4? 2. Alright, so let me plot these. At 2 it got to a, the -2. And at 4 it got over to a 2. Now you know what happens with these graphs? They bend towards the asymptotes. So take your pencil or your pen, and just swoon. This graph's just doing this. Woo! Woo! But now I can answer this question. In fact, did I have to make this whole graph to answer this? I only needed which side? I only needed the left side. I actually graphed too much, didn't I? That's okay. Wait to plot one extra point. Y'all agree? But now we can answer this question. So even though this is going to be asked in section not 2.2 but 2.6, we all can do this now. As you approach x equal to 3, from which side? So go jump on the function. Where? Way over here. You can if you want, but I say get really, really close to the what? To this tree. Jump on it and ride it, ride it, ride it, ride it, ride it. What's going on with that y value? Where's that y value going? It keeps going down and down and down and down and down. So what is that? Negative what?
Infinity.
Negative infinity. That's the answer. I'll put it right here. I just thought you'd be curious about that. I thought I'd show it to you now. That's in section 2.6. You're like, oh, I can do that now. Man, look at any graph, you'll find the answer. You can find a limit to it. Isn't that neat? I just need the graph. Cool?
So I guess you only have to understand the pattern, whether it goes up or down.
You got it. Now watch how good you are. What's this answer? Just look at the graph, right? What's the limit as x approaches 3? I put a plus there of 2 over x minus 3. Right it, where you going? Positive. Now, are these the same? No. So what has to be this answer? And I think you can see it in the graph. What's the limit as x approaches 3 of 2 over x minus 3? I heard it, the answer is 1. See, that's a powerful statement. As we indicated, these two would have to be the same. Now yes, this is true everyone. What if that was infinity and that was infinity? Then you could put what? That happens sometimes. That'd be one of these, or both of the two sides of the rational function went up like this. You go, oh, that's going towards infinity and that's going towards infinity, so the limit is infinity. Cool. Everyone, man, you were good with this. Everyone okay with that? Even though, when does this really get covered? Yeah, but why would we do it now, right? Isn't that cool? Hey, I got another cool one. Thought we'd hit it now. Here you go. Again, this is really in 2.6. I just thought it'd be fun to do it now. Get this out of the way. And when you see the picture of the graph, right? I'm telling you, if you know the graph, you can get answers. If you know the graph, you can get answers. What's the limit as x approaches? Let's have fun with that. The author thought you should wait till section 2.6 to do this. I'm like, nonsense. They can do this now. Let's write it. There's our picture. We see the graph, everyone. I think this has something to do with it. I think you all see it. Write it, but what x value are you approaching? Where is x equal to infinity? Way down there. So I wouldn't jump on the roller coaster. Get on there and ride it. Just ride it. Where are you going? I mean, this thing's not going down here, is it? What y values, they keep getting closer and closer and closer and closer to. You got it. So isn't this neat? With rational functions, it's just the Horace. Isn't that cool? When you're dealing with a rational function like this, and it's got a horizontal asymptote, well then your limit as x approaches infinity is the Horace. I'm abbreviating Horace as the horizontal what? Asymptote. Whatever that is, that's where it's going. That's what I mean. That's why I thought, you might as well see that. You go, if you're going to head towards the x equals infinity, you're heading towards the horizontal asymptote. That should be your answer. You bet it is. You bet it is. But not all rational functions have Horaces. Some have slant acids. Do you remember that? Like a slant asymptote. So we'll wait till 2.6 to do the slant asymptote thing. Yeah. So I went super job at that. There's another graph I got to do. That's kind of weird. This is 2.2. And we really hit everything in 2.2. One of my favorites is, I should show you this one graph. I don't put this on the test because if I use software to build this, I don't think it would look good. Do you have your textbook? You got it there?
Yeah.
Would you look at everyone, number 6? And there's something funny looking in the graph. Oh, this is page 96. Check it out. Just look at number 6, and you see something funny about that graph. I think every other graph you can be fine with. And if you try one of these at home, come in tomorrow, let me know if there was a graph question, like, what goes on with this graph? This is the only one I think people might have a question on when you go home. You know what it did? At one point, it did something like this. It looks like at x equal to, I think it's 5. The graph went like this. Like this. So I'm going to enlarge this. Everyone got me? Something kept what? Going up and down as it got closer. But I said I don't put that in dash. You go, why? Because I think I could use the best software. I still think you just get a blob of ink. Do you agree? Well, let's talk about that. Let's talk about this scenario. Let's just talk about that graph. Because we all know about sine of x, don't we? And what's the limit as x approaches infinity of sine of x? And this will help us, because doesn't that graph do something similar? The graph keeps doing what? What's the highest it gets to? 1. What's the lowest sine of x gets to? -1. But it keeps doing that forever and ever and ever. It keeps bouncing between what? 1 and -1. Does it go to one concrete value? No. So guess what I'm going to have to put for this answer?
Doesn't exist.
Does not exist. Y'all agree? So this idea of something kept doing this and doing this, as it got closer and closer to something, you're like, sorry, it doesn't exist, right? So that ink blob, when you look at it, you go, is this what it means? Yeah, it just kept saying it did this and did this and did this, so it wasn't going anywhere towards one number. But that's different from this. So when this was just going, as you went towards infinity, the limit was d and e. Do everyone agree? But what about a graph like this? We won't give it a name. But how about this graph? What if the graph did this? I'm just going to enlarge it. What if it did something like that? So it kept going like this, going like this, going like this, but it kept getting tighter and tighter and tighter, that number. Oh, well then we could say at x equal to, let's say, 10, as it was approaching x equal to 10 from the left side, it was approaching, I'll make this up, say like a 5. Okay, in that case, then we won't say d and e, because we can tell that it what? It was oscillating, but the oscillations between the what? The amplitude, going up and down, kept getting smaller and smaller and smaller and smaller and smaller, and it was getting closer to that. Does that make sense? That's what I just wanted you to see out of that. I didn't want that to bug you. Okay, what other graphs do I have to do for the end of class? Because I said I want to go up to graphing today. Well, there's still some graphs. You're like what? You ready? Absolute value functions. I wonder how to graph these. All right, you ready? Yes. Brilliant. V's. But what if? So I knew you all could do the V's, and very good knowing that. when he knows the absolute value graph alone looks like a V, like this graph right here. X minus 2. And we're not gonna do that limit, because I think you'd find it too easy. Find the limit as x approaches some number on this, well that just, first of all, it's continuous everywhere, isn't it? Do you know where this V hits the x-axis? Just set that equal to 0. Where's it hit? Right at 2. Cool. Awesome. So I don't think I should ask questions on this one. I think you'd always get it. It would just be the answer. The final limit as x approaches a number. You're just going to look at the number because it's all continuous, right? Like right there, here. I just think it's going to be too easy. So we're going to pick a harder problem out of the book. Final limit as x approaches 2 of that function right there. Well, I can see it. It's approaching what from both sides? 0. Oh wait. So we got to put the y value down. So I'm glad you brought that up. As we approach 2 from both sides, we always report the y value. So what y value was it getting closer and closer to from both sides?
0.
0. Does everyone see that? Cool. So we're like, okay, that's too easy. I'm doing a problem like, your author stuck this in 2.3, it should be back in 2.2, because we want to look at the graph on this. We're going to look at this problem. If it's odd, I know it's an even problem, so that's why I want to do it. I actually put this in, I thought it was a good practice problem, but it's even, so we can do it. X approaches 6. 2x plus 12. The absolute value of x plus 6. Let me make sure I copied that right, did I? I think so. Yeah. So after this, I think we should do a trig graph. Do something numerically, and that'll be it. But we should do a couple of these. So here's what we have to do. Because it's in a fraction, one of them is the absolute value bars, the other done. We got to tear this thing up. All right? So we're going to tear up this graph. Well, one way to do this is you're like, well, I can use my graphing calculator and graph it. Isn't that true? You absolutely could. Does anybody know where the ABS button is on those calculators? I go to catalog, hit second 0, just if you're curious. The second 0, what's it show? ABS, right? But I would like to show you what this looks like. So we're really going to kind of hit this thing a little bit algebraically too. So I'm going to go back to, what did I have up right before this? What absolute value function?
X minus 2.
You and I have to do a little pre-calc review. And we got to talk about how can you write that expression without the bars? Does everyone remember this? Don't worry if you don't. Might have been at least a year since you did this, right? I write x minus 2 down. Then I write x minus 2 again, but I put a negative on this. Okay? I put the word if. I put the word if. I can define that absolute value function in 2 pieces. It's called a piecewise function. And this is, look, I'll put an equal symbol. This equals these 2 pieces. It equals this if, and when I need you to set that x minus 2 greater than or equal to 0. X minus 2 is greater than or equal to 0. And it equals this if the x minus 2 is, take a guess. Less than 0. Now, do you want to improve that? What's a better way to write that?
X is greater than or equal to 2.
Yeah, write that, Owen. You might find that easier. I just wanted to show you. I just went back in there and said what was in the bars, and I said that had to be greater than or equal to 0. And I went back in here and I said what's in the bars, I said that had to be less than 0. Cool. So if you want to improve this, what was this again? X is 2. The greater than or equal to symbol, and this is a what? Okay, but guess what the graph does? It was what we had before. Oh, line with positive slope. What was going on before too? Line with a what? Negative slope, right? It's a bad looking graph. Just so you can match it up. And just to make that connection. That was that side? This side? Right? We get it. So, we need to find a limit as x approaches 6. And then when this doesn't have a plus or minus on it, does it? Let me make sure. Everyone My eyesight's getting worse by the year. And all the other math textbooks I'm fine. Stewart, it's just, you know the font size? Sometimes I can't see it. So I just wanna go back and double check he didn't have a little plus or negative on it, did he? This was number 42. I actually stole it from 2.3. I'm like, they should have put this problem in the last section. Nope, it looks clean to me. So this is number 42, is actually way up on page 107. Alright, there it is. Page 107, number 42. Well, I want to make this graph. Well, can you help me write this expression? What is this equal to? Well, this is equal to 2x plus 12 over x plus 6 if x plus 6 is greater than or equal to what? Is that what I heard? What's the other piece though? What's the other piece to that? 2x plus 12 over a negative x plus 6. If, and what goes here? Just look inside the bars. If the x plus 6 is what? Less than 0. So don't worry, some students come from a pure calc curriculum, they're like, I never saw this. I know, we had our course here, we actually included it with a supplement. I was teaching it this right before your class at 6 p.m. I was teaching this. You know, we did about 4 examples of this, and you get it. So anyways, can you clean this up? Can you simplify that? I bet you can. Can you factor that in simplify? What can you factor out of that?
X plus
Yeah, factor out the 2, you get x plus 6 over x plus 6, and what does this simplify to be?
2.
Oh, this is just a 2! No one see that? Let me write in case people want to say that's a 2, that's an x plus 6, that's all over an x plus 6. Cancels it out. So what's this function? If x is, what's a better way to write this? That's another way to write that right there. The x plus 6 greater than equal to 0. X is greater than equal to what? Negative 6? Yeah, I'll write that. So in here, let me just write this cleaner. We're saying this expression right here is just 2 if x is greater than or equal to a negative 6. But what's the other side? Can you clean it up? Oh yeah, what can you factor out of that? You factor out the 2, you got that little negative down there though. You get this x plus 6, you get this x plus 6. What cancels? So this equals this. So this is equal to this. So now it's equal to a negative 2 if what? This function is this graph if x is, but what does this say? X is less than what? So everyone take a guess. What does that graph look like? Now some of you might have hit on your graphing calculators. I thought we'd have fun doing it this way. So what do these graphs look like? Those aren't slanted lines. They're just what? They're just flat. So it's a flat line if x is greater than or equal to negative 6, and it's a 2. So right here, just go, and I closed the dot by the way, because it had an equal symbol. What's it doing if x is less than negative 2, or x is less than negative 6? What's it doing? What's the y value? The y value is always a what? A negative 2. So over here, now it's what? Flat that way. By the way, should I put an open circle here?
Yes.
Yeah, I'm going to put an open circle on that because it didn't have an equal sign there. By the way, it's impossible to put a dot over a dot because that wouldn't be a function. Do you agree?
Yeah.
It'd fail the vertical line test. By the way, now we know the answer. Would you just look at this? Find a limit as x approaches 6. Look, I don't have a plus minus here, so it means from both sides. The only way this can work is if both sides are heading towards the same number. Is it? No. So what's the answer? What's the answer to that question right there? Done and put D and E. Y'all follow me?
Yeah, I have a question where it says f, or 2 if x is greater than or equal to negative 6. What if, I understand you gotta have the equal sign on one side, doesn't matter which.
No, great question. I love it. I love it. He goes, you're gonna put the equals on one of these, right? And you're like, well, which side do I do it on? Well, I do this, but this problem, I like it because this originally had this set up. So I'll be honest, I actually just made a math error and you kind of caught it. I'm looking back at the original problem. This is from the textbook, everyone agree? Because that's the original expression. We all know the golden rule of mathematics. Denominators can never be what number? 0. So no matter what, does this function, no matter what, because this was the original expression, does this function really exist at negative 6? So everyone, you know what I'm gonna have to do? I'll have to tweak this, no problem, I'll still get the same answer. But I really should have an open circle there. Because, does everyone agree? There's no way this graph's function exists at x equals -6 because denominators can never be a what? 0, so I'll just take that off there. And thanks for spotting it, you know? But in other case, if it doesn't have a denominator down there, you just put that like that thing, you can put this on either side. It does not matter which side you put the equal sign. Cool. But I'm glad you spotted that when I had a little typo. Ah, then we had to write that little annotation in the video. I was like, whoa.
I just had no clue.
It's great, because, but you look at this, you go, this is the original setup of the problem. So we know in mathematics, no matter what, in any expression, the denominator at an exact point can't be 0 in the denominator, right? So that's how we know that nothing's existing at x equals -6. Right? You go, well, what if you simplified it? It wasn't simplified yet. That was the original expression. Now, would you try this on your calculators? I want to see how good they are. It only take a second. I was going to put it on the screen, but I was like, I'd rather you try it. How do you do it? Where's the ABS thing? Where's that ABS thing? Yeah, catalog. Go to catalog. It's the first thing on the list. You'd have to type y equals, and you go 2x plus 12, hit the division, and then you can do ABS, and it puts a parentheses, and then you put in parentheses to what? Now I have a typo on the board. What should I put around the 2x plus 12? Yeah, there you go. But I want to see how good your calculators. Who has an 83? That's really what I'm curious about. I wonder if the 84 is better than the 83. Did it do it? Oh, good. So guys, it works. So you could. This is my point. If you're stumped on a test, you see something like that, you're like, wait a minute. I know how to do limits. I just need to look at the graph. I just need to look at the graph. And if you're struggling with the algebra, pull out that graphing tool. Is it working? Or you can check it out. I was wondering if the 83 is just as good.
Yeah, it worked.
Cool. It didn't do a funny, goofy thing here. Sometimes I was worried about that. Nice.
Calculator keeps saying dimension.
Oh, let me look.
Or something.
Yeah, mine's
Yeah,
connected,
let's just
so-
see. One dimension
Oh, I
mismatch.
didn't enter anything. I just-
Oh, I'm gonna take that plot off.
Oh.
I'm glad you showed me that. You wouldn't be able to use it. Now you're fine.
Okay.
I got that.
Now, let me check the bottom here, make sure there's nothing in there.
My shit is
Good.
bad.
Sometimes there's stuff down there. Now it's gonna work. Just don't let that get highlighted. If it does, just unhighlight it.
I got this one.
Get the step plot on. We know that. Don't let your graph and the
I
step
tried
plot's
it
on.
before and I don't know.
Nice.
if it worked. I don't
You
know.
wanna do it?
Yeah.
So all I'm gonna do is I'm gonna do parentheses. I'm gonna do 2x plus 12, close the parentheses,
The whole thing.
divided by, now I need that ABS, don't I?
There has to be in parentheses.
It's in catalog, second zero.
Two X.
It's the first thing. And you just do x plus 6. Yeah. How's it look? Flat line, right? Cool.
Yeah.
To do that right there,
Yeah, I
Goodness.
guess.
I'm gonna do zoom 6.
If you go to Zoom,
Nice.
6.
Nice looking graph.
Standard zooming.
Did it work? Maybe I should have brought that thing, I could have showed it on there. Good. Is it, everyone, it's a little noisy, you know? It's a little noisy, but that's okay, we'll show this graph. After this, we'll do a sine graph, let's see how good it is. Can you hear it? Click, 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 click. Thing's a little loud, isn't it? Alright. Hey, just to project this, let me just grab that machine from the other side and we'll put it on there. This is so if anybody in here didn't bring a calculator, you just want to see it. This is only take a second. I'll just project it right on there. And you'll look at this thing and you'll see, a lot of you already made that graph. But you just want to see how is this thing looking when I put this on there. So you didn't bring your graphing calculator today? It's a piece of cake. You go in here and we're like, I want to verify this with my tool. Can I hit the lights? Alright, clear. Let me get that straight. And I'll pull this back so everyone can see that. Everyone see this thing? So I got a y equals. First thing I gotta make sure none of these plots are highlighted. That's for stats. So I just hit enter and it unhighlights that. Right? Zoom 6 gives you a nice standard window everyone if you just want to hit zoom 6. But I'm gonna type in I gotta start with the parentheses, right? Parentheses, 2x plus 12, close parentheses, division. Where can I get ABS? Second zero. So I'm gonna hit second zero and it gives me this ABS for absolute value, and then I just type the x plus 1. That's plus 6. Now if you want a standard window, you can just hit zoom 6. Zoom 6 is standard window, and I'll hit 1, let's just see. Let's see, was anything missing in there? Oh, that extra what? Good call, there had an extra parentheses in there. So zoom 6 this thing, let's see how it looks. Awesome, the only thing is, what's it doing there at the middle? It did a what? Connection, does everyone see that? Makes it look weird, like it's connected. Well, a lot of times you can go into like this mode, and when you see where it says like function, like if you, let's see if we do like connected, if I just do like, what if I did dots? Let's just see how it looks I did dots. Isn't that funny? So it's funny, sometimes like, this thing can be a little deceiving, and I didn't want it to trick you. Like you're like, we know that's the graph. But I made this look better by just going in the mode, and going here, I have an old TI-84, and I put it in dot mode rather than connected mode. Right? It's funny, you go, but it isn't connected, is it? This function's not continuous at x equal to -6. So that's just a bad calculator when it does that. That's wrong, isn't it? It is not doing that. So I just went to mode and changed connected to dot just to see, alright, yeah, that's what's going on there. And there's really open circles at either end, isn't there? Hey, thanks, Trey. I just wanted you to see that. Cool. Hey, so the remaining part to today is, can we do a trig graph? Is trig gonna be tough? Did everyone get a trig sheet? Throughout this week, we might be discussing some trig, because sometimes we gotta go back and remember that stuff. So, if any of that stuff in that trig sheet seems a little foggy, right? And you're like, I need to review that, then let's talk about that in class. So, didn't I do this? I did the sine curve, right? I did the sine curve. Okay, well then, let me draw it again. What's sine of x look like? I'm gonna give you a limit problem, and I'm gonna give you some kind of trig function. I'm not gonna do sine. What's the sine curve do right here? Yeah, pi over 2, and then a pi, and then 3 pi over 2, and then a 2 pi, right? So doesn't it go like this? Woo! Then down here it goes like this. How high did it get? 1. How low does it get? -1. What's it do on this side? Yeah, it just comes down here at negative pi over 2. What's it get to over here? Negative pi over here? That's far enough. I'm not asking about that. No, I want you to find this. Cardinal limit. X approaches, let's see. Oh, I got it. Pi. Now this function. Ooh, no, don't lay it. This is not intimidating at us. We can do this. Cosecant of x. How do you make the cosecant of x graph? It's a piece of cake if you can make that graph. Because that's his reciprocal buddy, right?
Yeah.
Sine of x is equal to, right? Or so I should say it this way, cosecant of x is equal to 1 over sine of x. They're called reciprocal buddies. So cosecant of x is 1 over sine of x. Well, what's its graph look like? I go off this thing, what do I make?
It's just gonna be flipped.
Yeah, you make these little hills. They're like these little parabolas like this. Shh, it's that one right there. And when here in yellow chalk is the graph of cosecant of x. What's it doing on this parabola? But this graph does have asymptotes. Can you all tell where the asymptotes are?
Pi to
No, you're good. Now you know why I asked you what's going on in pi. Alright, so this is just going to go like that wherever there's an asymptote right between these. Can you see it? But now I made the graph. What's the one as x approaches pi? From both sides. From both sides.
Doesn't exist.
Very good. But I think I should give you 2 of these, so here's my next one. Can you find the limit as x approaches pi from the left side of cosecant of x? Let's do it. As you approach pi from the left side, where's it going? Infinity. Nice. Good job. So I got another one. need is the graph. Who's his buddy though? Yep, cosine of x. 1 over secant of x is cosine, right? It's cosine x, right? Well, I just need to make the cosine graph and make those little hills. Well, what's a cosine graph do? Alright, let's see. 2 pi. 3 over 2, 2 pi. What's this graph? And by the way, I'll put these on that trig sheet so you can go back and review this stuff. What's this graph do? This graph starts at 1 in the air, it ends at 1 in the air at the 2 pi, and it's just kind of halfway at pi, it's way down here. So it went from here, halfway it got down to a -1, then it got back up to a what? 1. And it's smooth, it just goes, yeah, 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 yeah. Now where's the hills though for that secant of x graph? Where's the hill? I can see one here, where's the next one? Can anyone see it? Do this big. There it is. And when that's y equal to secant of x. I'm going to draw this graph. What's it do over here? Let me keep going. What's it do over here? Pi over 2. What's it get to down here? Negative pi. Q to negative 3 pi over 2. And where is this function at negative 2 pi? Let's back up. Now, when do you see the other hill? So where are the asymptotes? Oh, I missed this one. What's going on right here? Whoa, I don't want to go close. This thing goes right there. A tangent between them. There you go. So, everyone, what's the limit? As x approaches pi over 2, oh, and let me add something to this if you don't mind. How about from the right side? As you approach, look at the yellow chalk, get on this curve. As you approach pi over 2 from the right, where is it going? Good job. So isn't this cool, even though this stuff, we do this actually in 2.6, you can do it now. You just gotta look at things graphically. Isn't that awesome? So see, there's nothing that can stop you. I'm telling you, you go, oh, well what if that absolute value thing drove me nuts, right? Well, then you'll use your what? Calculator. Just maybe put it in that dot mode. It might be a little better. But is it okay you think it's simplifying those absolute value expressions? Hey, on Thursday when we're reviewing, feel free to holler at me and go, hey, can we do another one of those? And I'll just make something up like x plus 8 over absolute value of x plus 8. And you will see what we get. And it will limit as x approaches. If I do one side, you might get a number. I think if we do 2 sides, it's going to what? It's going to do one of these, isn't it? True? So I'll probably in the test just do one side. Hey, so, couple things. Would you just try that real quick? This right here. From the left. I'm just curious. Now, there are numerous ways to do this problem. Do you know how to break this into 2 parts? Sure. Which side do we need, the left or the right? So what's going on the left side? What is this expression equal to? On the left side, what is it? X plus 5, what's another way to write that? Ooh, big, very good. You put the negative there, and then I say if x is less than what? If x plus 5 is less than or equal to a what? 0. So when I now see my error, I meant to say the limit as x approaches a what? A negative 5 on the left. Alright, so if x is less than a what? And can I put the equal symbol?
But would it be,
Can I put that equal symbol?
fine if you put, if it's equal to -5?
Yeah, equal -5, right? Yeah, I love it. That's the better way to write it. Hey, can I put that equals? No, I can't, can I? Function won't exist there, true? So I'm just do a less, x plus 5 less than 0. Left side, right? Because we're doing left side. Which means, as you said a better way to write that. And I think it was a great point. You said better write this, x is less than -5. Cool. So this is what I have. Does anything cancel?
Yes.
Ah, then what's the answer? What do you think? We didn't make the graph, but we should get -1. Now look at your graphs, and you'll probably see that, right? And is it really going there? Alright, let's look. Pull this thing out, and just look at this thing. What we gotta type in here? Is this really going towards that? I go to y equals, alright, clear you will. What was the top? I went second zero for abs. It was x plus 5, what was in the bottom?
Regular x plus 5.
Just regular, parentheses. X plus 5. Ah, I did the connected. I'm gonna go to mode and make it what? It's still on dot, huh? It's still doing that. Well, we're gonna outsmart this calculator, right? I bet you I know what I can do. If I just did what? Let me see if sequence. Maybe sequence looks better with a bunch of dots. Can everyone see those little dots in there? I actually show the little dots in there. But yeah, that graph, I could still see it work. That was at -1, but it did make that little piece together there. Cool. Hey, here's the last problem I wanted to do with you today. Absolutely, feel free to do this. I always like to tie in what we're doing today into something we're gonna do tomorrow. What's the only way we were focused on all day today on limits? What technique? Finding limits graphically, right? And I bet you're an expert. Just make the graph, look to see what's going on. If both sides meet from the left and the right side, then the two-sided limit exists, right? Well, I put up this problem earlier. Is this right? I'm hoping. Did I have this?
Yeah.
And I wrote 3, which side did I do?
Probably from the left. Yeah, from the left.
Okay, so half hour ago I had this problem. This is how I went to end class today. Limit x approaches 3 from the left side. We did this which way? How did we find this answer? We made a graph. It works! But is that the only way to find limit answers in mathematics? You go, no. There's another technique. It's tomorrow. I just thought I'd give you a tie and then we'll break and get out of here. There's another way. We know graphically.
Isn't it based off the degree, like the power?
Ooh, I love it.
Basically, you just sub in numbers.
I love it. You all are great because you just start subbing in numbers. We just want to know what's going on as you get really, really close to what number? 3. From which side? From the left. So, and can you just help me out? Brainstorm right now. We're just going to plug it in to see this answer. All right, we'll match it to the answer we got before. I am not making a graph. I'm going to find this limit numerically. So what's the number really close to 3 from the left side of 3? So you got to think of a number line, everyone. Here's the number 3, but over here, really, really close. 2 point what? 2.9. Go better. Go better. I like that. I like that. I like what you just said. How about, let's plug it in here, 2.9999 into my calculator. Alright, so what is on the calculator? 2 over 2 point, he said 9999, you can put another 9 if you want. And just, I want to see this number. Is it really, really huge? Or is it really, really huge and negative? And we should get an idea of what's going on with this actual graph. What comes out on this calculator?
Got negative 20,000.
That's huge and it's negative. Where do you think this thing's going?
Negative.
What's it heading towards? Just from that one little plug, you and I have a sense of what's going on here. That's a very, very, very large negative number. It looks like this is heading to what? Is that what we got before? So that's called finding limits numerically. Absolutely you can do that. Absolutely, that's full credit for justification on a test. You know, I applaud you. I'm like, it's good thinking. Students do that all the time. So we always think that way too, right? Awesome. Hey, great job today, everyone. We'll do that tomorrow, but that's a great way to think. So there's 3 ways to find limits. We haven't done the algebraic technique. We'll spend 1 class for that. That's 2.3. Have a great day.
Great night.